Hi guys, I'm John Michael, the lead dev at Hub and the founder also. Today I'm showcasing Drainage Lab. What is Drainage Lab? Uh, I will define it as a hydrodynamic engine built for civil and drainage engineers. Uh, Let me say, who need absolute precision. Now, in this video, I'm going to walk you through the interface and demonstrate how we solved the industry's biggest browser-based physics challenges by bringing a fully defensible and steady Saint Venant solver directly to your web application. That might be a bit braggy. Okay, so on the left sidebar, we have our tool palette. Also there we have our solver settings, and in the center we have our network canvas, and at the bottom we have our results hydraulic profile, basically just the analytical dashboards. And I'm going to walk you through uh, templates that we've chosen specifically because it explains a clear difference between our two methods that we are using here, which is steady state and dynamic wave. Now, it represents a flat coastal region where gravity-driven drainage alone is basically impossible, or let me use the term physically impossible. Now, rain runoff from the estate collects into a wet well, and a centrifugal pump lifts the flow over a levee uphill through an adverse slope rising main to the outfall at the sea. So here you can just zoom in, look at it, zoom out, check the entire. So let us run it. We are running using the steady state. Now, steady state here, it is great for baseline check for pipe capacity, but it has severe limitations for complex systems. Let me just run it. Uh, and then let us use the hydraulic inspector to check the rise and fall. So it is used for just checking pipe capacity. Now, it assumes the pump is running continuously and at a static flow. But in the real world, it doesn't. A pump doesn't run forever. It cycles on and off as the wet well fills and empties. Uh, Now, steady state analysis, it completely misses this. The storage attenuations, the dynamic backwater surges, etc. It misses them all, the transient timing details. And that's why we have the other option, the dynamic wave solver. Now, for the dynamic wave solver, uh, here now we get the the real thing. Okay, let's get to the dynamic wave solver. Now here we get the real thing. uh, we get to watch the storm play out. We see the wet will fill up, watch the pump cycle on and off automatically as the water levels trigger it, and also inspect the transient backwater waves in real time. Okay. Uh, so I think let me just run it. Good. And then just run the hydraulic inspector. So you can see how it's moving on the map. So you see the correlation is divergent, okay? Uh, I don't know. Let me just explain to you guys what is going on, just a little bit of what is going on. Now, this solver is executing an implicit neutron-Raphson junction solver to find the exact quadratic intersection of the pump's head loss curve and the system's dynamic head on every time step. Now, with this, we are able to see the flow climb and stabilize as the head changes. Okay, and we are also modeling localized minor losses. This is done by defining junction loss coefficients. And say we also use semi-implicit friction update to calculate minor head losses, uh, which is k v squared over 2g, I think. And because it's integrated semi-implicitly, it remains unconditionally stable even during rapid pump startup surges. So basically, we are saying as the wet well drains, the pump cycles off at the low level trigger, and it shows the exact drawdown curve. And say to guarantee the stability uh, without having to guess a time step, we utilize an auto CFL adaptive time stepping. This continuously monitors the maximum cell wave velocity and adjusts the simulation time step dynamically. This ensures that the CFL number is kept under 0.95 to capture the sharp wave fronts cleanly. Now, we have benchmark suits, and all of them have passed with less than 5% mass error. So we can tell you that the system correctly honors a full 1D and steady flow equation, and it is suitable for professional engineering defensibility. You don't have to take my word for it. You can come and try it out yourself. It's engineering update engineer, design materials page, under extensions, drainage lab. Now, with these implicit pump curves and the minor loss coefficients and the unconditionally stable VM routing, I believe uh, this is very accurate, defensible, and interactive. Uh, and it's right in the browser. It's very great. So you can explore the templates, run your own scenarios, and experience, let me say, next generation of stormwater storm drainage design, or this generation of storm drainage design. Okay. uh yeah, I think that's all. And I want you to know the difference. The fact that the correlation is divergent doesn't mean that it's wrong. It's actually supposed to be divergent because they do different things. mm. That one is for pipes, this one is now the real play, but you can go and check it out. uh, okay, try it and build with confidence. Reach out if you have any questions to support at engineeringhub.engineer. We are always on the lookout for email.